so we're going to go ahead and finish up 8.1 today, and we'll pick up from where we left off on example number 6. So let's go and see if we can do example number 6. This is quite a fun question. It says from noon to 6, the rate at which people enter the amusement park time t is given by e of t, and that is given on the left-hand side there. And also, when people are the leaving rate is L of t, and it's given in an actual equation. So if 3,000 people were in the park at noon, how many people are in the park at 6 p.m.? So rounded to the nearest 100. So what do we have to find? We have to find, so basically what we're going to do is we're going to do E of t, and we're going to subtract the people who leave. These are people who enter, people who leave, right? And we're going to do this from 0 to 6. And then we have to add the initial amount of people, right? How many people did we start with at noon? We started with 3,000. So this is what we're looking to do here, okay? This is what we're trying to find, okay? Because this is what we initially started with. This is the amount of people that entered. This is the amount of people that left, right? So here we go. So we're going to do what? 0 to 6, E of t dt minus 0 to 6, L of t dt plus 3,000, okay? So let's do this guy here first. E of t, if you look at E of t is not actually, that's actually if you want to, it's a piecewise function, right? But more importantly, to find the area under the curve, what do we need to do? We're basically counting squares here, right? We're counting squares, so the way we're going to do this is that we're going to have what are we going to have? We're going to have trapezoid number 1, we're going to have rectangle number 2, and trapezoid number 3, right? So trapezoid number 1 is this leg plus this leg. So that would be what? That would be 400 plus 600. So that's 400 plus 600 divided by 2 times the base here, or the height. And the height is 2 plus, this rectangle is, what, 600 times 1. And then the last trapezoid is 600 and 500. 600 and 500 with 2 hours, so 600 plus 500 divided by 2 times 2 hours. Wait a minute, is this 2 hours? The first one is actually 3 hours. This is 3 hours, right? 3 hours here, 3 hours here, 1 hour here, 2 hours here, add to 600. Okay, so what do we get here? We get 1,500, so that's 1,500. This is 600. And this is 1,100. We add them together. We get what? 21, so we get 3,200. So basically we find this guy to be, 3,200, right? 3,200. And we add that to the 3,000, what do we get? We get 6,200, right? So we're going to get 6,200. So all we have to do is 6,200 minus 0 to 6 L of t dt. Okay? So let's go ahead and figure this guy out. Okay, we figured out how we're going to figure that guy out. L of t is given to us as L of t was 52 minus t squared e to the negative t over 5 dt, right? Well, the first thing I would do is pull the 50 out, go like that. So what do we have here? Well, this guy is simple, right? This is 2t when you do the antiderivative, so that's easy, right? What do we have here? What do we have on the back side? Well, this is our good friend, what? This is the integration by parts, right? Integration by parts. As a matter of fact, you're going to do integration by parts twice. Because in order to solve, so if we solve this guy, this is going to give us this e to the something, some number here. I don't know what, there's a number here, right? Plus dt plus some other stuff here, right? So we're going to have to do it again, all right? So you're going to have to do it twice. Or, if you remember, if you were that one of the 1 to 3% of people who remembers this, you can actually do what? You can actually do tabular form, right? Tabular form, remember I told you that tabular form was kind of like a gimmick, that you would probably not remember it anymore. Okay, so let's go back and just kind of refresh our memory here, right? So we're trying to find this guy, right? And we know that we're going to do two different, so if you remember correctly, we're going to put this into two different functions, and one of them we're going to take the derivative of, the other one we're going to continue to take the integral of, right? So t squared, and I'm going to do e to the negative t5, right? Okay, so I want to differentiate this guy, right? So I differentiate this guy, there's endless, nothing happens, right? And I integrate this, it keeps on going from t squared to t third, t fourth, t fifth, t sixth. There's no end to it, right? So I want to differentiate this guy. So if I differentiate this guy, I get this. Differentiate it one more time, I get this. Differentiate it one more time, I get 0. Okay? Over here, if I take the integration of this, so if I integrate this once, I'm going to get this, right? So if I take the derivative of this, the negative 1/5 that comes down here cancels out with this and becomes this. So I'm going to integrate this one more time. I get what? 25. Right? If I integrate it one more time, I get negative 125. Right? Okay. So maybe you remember this far, okay? So what do we do next? And I have to multiply this, this, and this, but this is plus, negative, and plus. A lot of ways that this can go sideways for us, right? So if I do this, what do I get? I'm going to get this guy, this times this, so it's minus 5t squared e to the negative t to the 5. Then I do this, I get negative 50t e to the negative t over 5. I go here, I get negative 250 e to the negative t over 5. Okay? So this guy is going to become basically this. Obviously, since it's an indefinite integral, I'm going to get the c at the end, right? Okay? So I can go and put this in. So now, since I know this, I can go ahead and use this and put it in here. So I'm going to go, this is going to be equal to 50. So now what am I getting? I'm going to take the integration. So I'm going to get, this is going to be 2t minus this guy, right? So what am I going to get? Since I have to subtract this, it's going to be plus 5t squared e to the negative t over 5 plus 50t e to the negative t over 5 plus 250 e to the negative t over 5, like that. Then I can go from 0 to 6, right? So that's what I'm going to get, right? And I'm not going to bore you with all this, so we can go and put this in, and we do this. And if you do that, what do we get? We're going to get, according to the book, we get 2106. This becomes 2106. If you remember correctly, we were at this. where we calculate this guy to be this, so this is going to be equal to 6200 minus 2106. So I'm going to get 4194. Is that correct? 4194? 4094. 4094. So that's going to be your answer. Okay? Again, so this is kind of a clever, good question because it has you do on the leaving side an actual equation, but on the other side you have to look at the graph and realize that it's just area under the curve and count the squares. Okay? Or of course you can just nint it unless I ask you to do it algebraically on the test. Okay? So that's 6. So let's do example number 7. Example number 7 is finding gallons pumped from rate data. Okay, so it gives you a running rate as you're pumping out something or water or something or whatever it may be. So the pump gives out that certain rate. And you want to find how many gallons were pumped during that hour. So you have to basically, you're adding, it's giving you, starts at 0, you get 58, so 58, and then it goes, and it gives you a rate, and you have to calculate everything under this curve here, right? All right. So basically what we're going to do is we're going to use the trapezoidal rule. Okay, we're going to do the trapezoidal rule, and we're going to do that. Okay, so if you remember, so let's go back and see if you can remember. What do we remember about the trapezoidal rule? The trapezoidal rule was what? The trapezoidal rule is basically 1/2 of LRAM plus RRAM, right? In other words, if you remember, it was H over 2, and then we had Y naught, or I'm just going to go ahead and abbreviate it this way, plus 2y1 plus 2y2 plus 2yn minus 1 plus yn, right? In other words, the last two were only 1. Everything in between you got added, you did it twice. Okay? So, and basically, all you need to do is just plug and chunk those in there, okay? Now, questions like this are very popular on the AP Calculus test, and the reason why it is popular is because it requires you to analyze data, and it gives you just data, so you have to do more than just plug and chunk into an equation. Okay? All right. So I'm not going to go over that one. That one's pretty simple. Let's do example number 8. Example number 8, we have the gopher problem. We have a 10-mile stretch of rural Minnesota road is bounded on the north by colonies of pocket gophers. Along the road, the density of the gopher population is 500 per square mile. The density increases linearly until it reaches 2,000 square miles, 3 miles from the road. So in other words, I have a road here, and when it starts over here, it is 500, and as I go here, 3 miles, at here it becomes 2,000, okay? So I have to be able to, and it's going up linearly, and I'm looking at a 10-mile stretch here, right? 10-mile stretch. I want to find out how many gophers are in here, okay? So from 500 to 2,000 as y increases, and it increases linearly, so obviously it is a linear equation. So we're going to have starts at 500 plus some sort of rate here, y is going to be equal to, at the end it's going to be 3,000, right? When y, not 3,000, 2,000. 2,000. So when y is equal to 3, I'm going to get 2,000. So I move this over, I get 3a is equal to 1,500, so a must be 500. So basically it's going to be what? I'm going to get starts at 500, and every mile I increase 500. So it's going to be 500y. Okay, so this is the linear equation for that. Okay, so I'm going to get 500 plus, and this is what? This is the density per square mile, right? So my per square mile, so I'm going to have to multiply this by 10 times whatever little dy I have there, right? Okay, I'm going to do this from y is equal to 0 to 3. Okay, it's pretty simple. So if I do that, what do I get? If I take the 500 out and the 10 out, I get 5,000, 0 to 3, 1 plus y dy, 5,000, this is going to be y plus 1/2 y squared. I'm going to evaluate this from 0 to 3. So when it's 3, what do I get? Oh, this is times, right? So if I times, I get 3. When it's 3, I get 3 plus, this is 9 over 2, so it's 4.5, so it's 7.5. And then when it's 0, it's just 0. So it's going to be this times 7.5. And if I do that, I get 37500. 37500. That many gophers. Lots of gophers. Also, it kind of makes sense, right? As you go further away from the road, you would have more gophers, because the closer you are to the road, you're going to get killed. Okay, and then last but not least, we have a work example. So let's go to example number 9, a bit of work, So before that, it kind of walks you through Hooke's law. Hooke's law is, for those of you who've taken physics this year or with me a couple years ago, Hooke's law says that F is equal to K of X, where K is Young's constant. Young's constant, who actually worked with Hooke to develop this equation. Basically what it says is that if I have a spring here and I have a thing here, I pulled it out. If I pull this out, X, the distance, if I pull it out X, it'll take, to pull it out X amount, it takes F amount of work to do that, and that is dependent upon Young's constant, which is dependent on the actual material of the spring itself. Okay? So, in example number 9, it says it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done in stretching from its length? So, in other words, it takes 10 newtons to stretch it out 2 meters. So, K is going to be equal to 5 Newton per meter. So to find the work, I have to do this. So it's going to be what? K is 5x dx. And I'm going stretching out from where 0 to 4. Doing from 0 to 4, right? 0 to 4. 0 to 4. So I'm going to get what? 5 over 2x squared. 4, 0, so when I get 4 squared, I get 16, divided by 2 is 8, 40 newtons, 40 Newton meter, actually. Okay, so there you go. And with that, we'll finish 8.1.